So thanks to the organizers to giving me the opportunity to talk today. And so today I want to talk about on the number of ideas which norm is a binary form of degree 3. So let's start by fixing some notation. So in Urtalk, K is a cyclic extension of Q of degree 3. K is a non-trivial character of the Galois group of K over Q. And Q is the conductor of K. F is a binary form of degree 3. We denote by R a domain of R2. And for a positive real number Xi, R of Xi is the domain R, which is dilated by the factor Xi. In this talk, we look for an asymptotic estimate of this function Q of Xi Rf, which is denoted by this sum, while the quantity R3 counts the number of ideas of OK of norm n. Because we are in the case of cyclic extension of Q, we have the following equality for R3. R3 of n is this function, where this symbol is the convolution product, which is given by this equality. So before establishing the main theorem, we make 4 hypotheses on the domain R and the form F. First, the domain is open, convex, and bounded with smooth boundary. Second, we have for all x in R, x is less than 1. The norm of x is less than 1. Then f of x is also less than 1. And the fourth hypothesis is the form F is irreducible over K. And under those hypotheses, we have the following asymptotic estimates, which is that Q of FCR is K of F, this product of L function, volume of R, C2, plus a big 2 of C2 over log C with a small power. And we can write K of F, which is equal to KQ of F, where Q is the conductor of key, and product of KP of F for P not divide Q. And also we have some explicit expression of KQ and KP, but I don't talk, I don't speak about this. Here, I will speak later about this expression. And the last assertion is, if the ring OK is principal, we have a geometric interpretation of the constant KQ of F and KP of F. So the proof is based on methods developed by Lartaux and Tenenbaum. And so to prove it, we need some results on an arithmetic function called Hooley's delta function. So what is Hooley's delta function? For an integer n and 2 reals, we can define delta 3 of n u1 u2, which is this sum, when the divisors de are between exponential ue and exponential ue plus 1. And delta 3 of n is just the maximum of the x function of u1, u2. A theorem enunciated by Hooley and Tenenbaum 9085 gives us an upper bound of the mean order of delta 3 of n when we ponderate by a nice function g. And what I call a nice function is a positive and multiplicative function which satisfies the prime number theorem with mean value over prime equals to 1. As an example, in our case, if we put f tilde of x, which is just f of x1, then the function rho f tilde, which counts the number of roots of f tilde mod n, is a nice function because f tilde is irreducible over Q. But we can also take in this function delta 3 two other arithmetic functions in arguments. This is led us to this equality. And now delta 3 takes in argument seven arguments. And we take V1 and V2 because the functions f1 and f2 are not necessarily positive. So delta 3 of n f1, f2 is the maximum over u1, u2, v1, v2 of this function of 7 arguments. And now I will give a new theorem which upper bound the second moment of this function, of this new function delta 3. If Q1 and Q2 are non-trivial characters, such one Q1, Q2 bar is non-trivial, then for good arithmetic functions, we have this upper bound with the factor rho is just near of 0.218. And what I called a good function, as previously, is a positive multiplicative function, which satisfies a prime number theorem for a prime number theorem with mean value over prime is equal to 1. And also the following equalities: sum of g of p f of p is big 2 of x exponential minus c square root of log x for f is equal to q1, q2, but also q1 over bar q2. Now I will tell you about the sketch of proof of the theorem. So in our case, f tilde is also a good function because f is irreducible over k. So what is the strategy to prove the theorem? We start from the convolution identity for the definition of L3 to write Q as the second sum with the set lambda is denoted by this one, lambda of SF, which is just the set of tuple Mn such that S divide F of Mn. And to prove the theorem, we need a good approximation of this quantity. To do that, we denote by a rho f plus of S, which is just the number of tuple AB such that S divides F of AB. And we can enunciate the following lemma due to Stefan Daniel. If we have a binary form of degree 3, then the quantity lambda of D1, D2F intersected with R of C is well approximated by this quantity. And so we have a very good approximation of this quantity. When the number D1 and D2 are well bounded. We can use two corollaries. Before announcing the corollaries of these results, I have to say you that the proof uses an approximation of the number of points of a lattice in an open domain convex. This is why we need H1. And also the proof uses the theorem of Hooley and Tenenbaum on the function delta 3. Then we can enunciate two corollaries of these results. First, we have also a good approximation of this function when only the product is bounded and D2 is between exponential u plus 1. And the second corollary of this result is another good approximation when only the product is bounded. So in the equality of Q of CRF, we have a good approximation of this term when D1 and D2 are well bounded. So what happens when D1 and D2 are not bounded? In this case, in the sum of R2 of f of x, we want to make a change of variable, putting D3 is equal to f of x over D1, D2. But this change of variable is only efficient if the character of f of x is equal to 1. So this is the next step of the proof. This is to give a parametrization of Q according to this equality. So to do that, we note that for n such that which is prime to Q, then we have R2 of n is not 0 if and only if K of n is equal to 1. And also we have if all the prime factor of D are prime factor of Q, then R2 of Dn is equal to R2 of n. With these two conditions, we can parameterize Q with the condition of K of f of x is equal to 1. And this parameterization is given by this big formula. So this polynomial f beta d1 d2 and this set r beta d1 d2 are bit from f and r by linear transformation. This set W is a set of some root of polynomials mod d du q. And the most important thing is G1, which is the kernel of K. And so this is the set of alpha in Z of your QZ times such that K of alpha is equal to 1. And so this set G1 gives us our parameterization, and Q2 is just this sum, but in our case, f beta d1 d2 and r beta d1 d2 are built with respect to the condition of all the tuple f mn in Rx satisfies key of f of mn is equal to 1. And so we can make our chain of variables in our sum. So if we want to estimate Q2, now we can change, we can make our change of variable. So we put four parameters, Z1, Z2, Z3, and Z4, with an exponent delta which is equal to this one. And we make the following partition over the sum. The following partition is the following. We have 8 domains, and in each 8 domains, we can estimate with lemma or corollaries and change of variables. So in the domain D1, we can use the lemma. In the domains D2 or D3, we can use the first corollary. In the domain D3 and D6, we can use the second corollary. In the domain D7 and D8, we have to make a change of variables. And after, we can use lemma or corollaries. It remains the domain D5. In the domain D5, we can't use lemma, corollaries, and change of variables. And this is why we need the theorem of delta function twist by 2 characters, because this is it which will give us our estimate. And the last word on I will say about the proof is only the set of D1, D2 which are in D1 or D8 counts for the main term of the theorem. The other domains contribute to the error term. Now, what happens if OK is principal? If OK is principal, the norm of an ideal E is equal of the norm of an element A which generates E. This led us to put a Z basis of OK and build a polynomial with this Z basis, which is only given by the norm. And what we can prove is, in this case, KQ of F is equal to a product of KP of F. And we have the geometric interpretation of KP of F, not only for P divide Q, but for O prime P, which is KP of F is this quantity. So how to prove that? So the explicit expression of KQ of F found in the main theorem is the following. This is unconditionally to OK is principal. And the set E of QK is given by the cup of, for alpha in G1, of those sets. And remember that G1 is the kernel of key, which is a subset of Z over QZ times. and so G1 is the number of is the set of alpha such that key of alpha is equal to 1. So this is quite important for the domain E of QK, and so for the constant KQ. And in our case, because OK is principal, we have the following lemma. Which says that the following properties are equivalent if n and q are primes, which is key of n is equal to 1, and there exists a tuple such that n is p of this tuple but q. But the second condition is a local condition. We have only to, that is to say, we have only to verify this mod p power vp of q for all prime p divide q. And because this is a local condition, that allows us to break kq on into a product of kp. So it remains to compute to prove that kp is in this form, and to do that, we have to give an explicit computation of those sets for a generic A, and this computation needs the decomposition of POK into prime factors. In this case, because P divide Q, POK is three times a prime ideal. Is 3 times a prime ideal. And also to complete this set, we need that this prime ideal of the only prime ideal of POK is principal. Now, what happens when P not divide Q? In this case, the expression of Kp of F is given by this big formula. And as for P divide Q, to find this equality on Kp of F, we have to compute the same the cardinal of the same set for a generic A, and the computation of this cardinal needs the knowledge of the prime factor decomposition of POK. And this prime factor decomposition is given by the value of key of P. If key of P is equal to 1, then POK is the product of 3 prime ideals. And if key of P is not equal to 1, then POK is prime ideal, is 1 prime ideal. And I will stop my talk here. Thanks for listening.
Thank you very much. So let us all unmute and thank our speaker.